Okay, so the last period before your test the other day, we had discussed all the different types of all the different types of movement or molecular movement that things can undergo. So vibration, rotation, translation, and how gaseous particles being able to move in all three different ways have the most entropy and have the most microstates, etc., etc. Okay, so here are some examples. You guys can go ahead, pause the video, predict the sign for the delta S for these, and I'll go over them, predict first, and then play the video, okay? So in the first one, you have water, um, gaseous water becoming liquid water. So you have a phase change where something with more molecular or atomic movement is going into a state of less movement. So we have a negative delta S here, okay? The change in entropy is negative. Then solid carbon dioxide subliming. So sublimation is a process where you go from solid to gas without passing through liquid, okay? So you skip the liquid phase, you sublime directly into gaseous phase. So that's why you have dry ice and you see like the smokiness coming out of that. That's actually the solid CO2 subliming into gaseous CO2, okay? So you're going from a very restricted to a very non-restricted phase. So delta S for that is positive. Then the next one is a full reaction. So when you have a reaction like this, it should also be in the gas phase. Nitrogen is gaseous, as you know. You have dinitrogen monoxide. You have 2 moles of that going into or decomposing into 2 moles of N2 and 1 mole of O2, you are actually increasing the number of moles of gas. So greater the number of particles, greater the microstates, greater the entropy. So you have a plus delta S for that. Then boiling of water, you are changing from liquid to gaseous phase. Entropy change is positive there. And in number 5, you are going from solid calcium carbonate to solid calcium oxide and carbon dioxide gas. You have a mole of gas here, okay? And that means gaseous particles have no microstates. You have a plus delta S there, okay? When you're talking about this equation, we will at some point talk about how more complex molecules have more entropy just because of the way that those bonds can stretch and bend, just because of the way that those quanta of energy can be distributed between all the different atoms and whatever, okay? But in this particular case, more moles trump less number of moles, and because of that, you have a greater um, entropy in the products. Okay, now, so we know that the criterion for spontaneity is actually an increase in the entropy of the universe, right? That is why things that are possibly endothermic still happen, because the entropy of the universe must be increasing. And when we are thinking about things like when you're looking at from the perspective like water freezing, you're going from a liquid water to solid water, you are definitely decreasing the entropy of the system. Even though you're decreasing the entropy of the system, the entropy of the universe overall must be increasing. And as long as the entropy of the universe increases, you will have a process that is thermodynamically favorable. Okay, so in this particular case, second law says for any spontaneous process, the entropy of the universe increases. So as long as delta S for the universe is greater than 0, you will have a process that is thermodynamically favorable. All right, so here is a kind of a graphical representation of that. You have the delta S of the system, which is negative right here. The delta S of the surroundings is positive. And because the delta S of the surroundings is positive enough to overcome the negative delta S of the system, you end up with this overall delta S of the universe that is positive, okay? So the delta S of the universe is made up of the sum of the change in entropy of the system and the change in entropy of the surroundings. If this one is negative, this term right here is negative, and this term right here is positive, positive enough to overcome the negativity so that the overall solution is positive, you're going to have a delta S of the universe that is positive and therefore thermodynamically favorable. Okay, so why is the entropy of the surroundings positive is the question. Okay, so when something, I'm trying to see if I would address this later on. Yeah, okay, so when you are freezing water, you have liquid water that is releasing thermal energy into the surroundings, and that release of thermal energy is actually increasing the entropy of the surroundings, right? You're adding thermal energy to the surroundings. That means you are increasing the number of microstates in your surroundings, and because of that, you will have a greater change in entropy of the surroundings, which means you will have a delta S positive for the universe. Okay, but this whole thing where you're looking at it from the perspective of the surroundings, that kind of tends to be temperature dependent, and we're going to talk about that in a second. Okay, but generally, if you have an exothermic process or reaction, that is going to increase the entropy of the surroundings, because if you're the system and you're releasing thermal energy into the surroundings, you are increasing the number of microstates in the surroundings, which means, because energy translates to kinetic energy translates to the different types of molecular motion. So, and faster motion, more collisions, whatever, different microstates, more microstates, and therefore exothermic processes and reactions contribute to increasing entropy of the surroundings. Endothermic things that remove thermal energy from the surroundings contribute to a decrease in entropy of the surroundings, and you are lowering basically the way that energy can be squirreled away in different molecules in the surroundings. Okay, so it's really a matter of perspective whether you're looking at it from the system or the surroundings, but we're trying to stick to the system because you can track energy changes between the system and the surroundings from the system's perspective. Okay, now the delta S of the surroundings, or the change in entropy, or the magnitude of change in entropy of the surroundings, is dependent on temperature. Okay, so imagine water freezing. You always think of kind of like winter, right? The freezing of water, or putting water in your freezer to get ice cubes, whatever, right? You always have to have a colder temperature, and it has to be colder than 0 degrees Celsius, right? 0 is water's freezing point, which means that is when water starts to freeze. So below 0 degrees, water will freeze, right? So if the temperature is above 0 degrees Celsius, water doesn't freeze, even though it is an exothermic process and it's supposed to be increasing the entropy of the surroundings. If it is 1 degree Celsius, water won't freeze. So the question is why, okay? At 1 degree Celsius, the delta S of the surroundings is apparently not big enough to counter the negative delta S of the system, which is going into a more ordered state because we're going from liquid to solid. Okay, so think of an example. So imagine you have $1,000 and you're feeling super generous, okay? And you want to give this away. And you find someone that is very poor, let's say no money at all, you're a homeless person, okay? If you give your $1,000 to the homeless person who's very poor, very lack of financial supplies, right? That would make a huge difference to them. That $1,000 would make a big difference to their lives. But if you give your $1,000 to, let's say, a billionaire, that's like a drop in the pond for them, right? Your $1,000 is pocket change for a billionaire, right? So the environment into which the thermal energy dissipates into, the thermal energy in this case is obviously $1,000, it dissipates into, it matters. So if you send some small amount of thermal energy that is released in the freezing of water into a colder environment, it's going to matter more. The change in entropy is going to be much larger then if you release that same amount of thermal energy into a very hot environment, okay, it won't even feel it. The microstates won't really be even affected because there's already so much thermal energy in the environment. Like, let's say a hot summer's day, water doesn't freeze because the delta S of the surroundings is almost negligible. If water is trying to freeze, and that amount of thermal energy being released won't affect the temperature of the surroundings or just the setting of the surroundings at all. But if it is cold, if the surroundings are cold and water is the system, and it's trying to release that thermal energy into the surroundings, because the surroundings is already so energy deficient, that small amount of thermal energy is actually going to cause a greater change in entropy, that way greater change in entropy than it would even at 1 degree Celsius. Okay, so that is why water freezes at 0 degrees or temperatures below 0 degrees. Okay, so smaller the entropy of the surroundings. No, you have to read it the other way. Higher the temperature, sorry, smaller the entropy of the surroundings. Okay, because or the change in entropy of the surroundings. If you have a high temperature, if it's a hot summer's day, it doesn't freeze because your tiny little contribution from the freezing of water doesn't really have any effect on your surroundings. Okay, so remember that entropy is a measure of energy dispersal per unit temperature. So if the temperature is very high, it doesn't really cause any effect into the surroundings. Okay, so little graphic graph showing how low temperature and high temperature are affecting the deltas of the universe. Okay, so if you are in low temperature surroundings, the delta S of the universe could be spontaneous because the delta S of the surroundings is large enough to overcome the delta S of the system, which is negative. But if you are in higher temperature surroundings, then the delta S of the surroundings does not account for enough to overcome the delta S of the system, which is negative. So the delta S of the universe is negative. Therefore, this process is thermodynamically unfavorable, temperature dependent. There are some processes, doesn't matter what the temperature is, it will never become favorable. Okay, not favorable at any temperature. You can calculate that. I'll teach you how to later on. Okay. Now there is a little way of quantifying entropy changes in the surroundings. Remember, surroundings is no good. We want to do things in terms of perspective, from the perspective of the system. Okay, so you know that the system exchanges heat with the surroundings. It leads to a change in the entropy of the surroundings. Okay, and we know that at constant pressure, which is kind of where we're living now at constant pressure, we know that the heat of the system, Q of the system, can be used to quantify the delta S of the surroundings, because thermal energy being released by a system is going to affect the entropy of the surroundings, right? So a process that emits thermal energy into the surroundings, where Q of the system is negative, increases the entropy of the surroundings. This is temperature dependent, but we know it does increase it. If it's a process that absorbs thermal energy, it decreases the entropy of the surroundings. Now, because of that, we can say that the magnitude of delta S of the surroundings is directly proportional. That's the sign for proportionality. The delta S of the surroundings is directly proportional to the magnitude of the heat released by the system. Okay? So the negative sign here is indicating thermal energy lost from the system, which is directly proportional to the change in entropy of the surroundings. That's the proportionality sign. Okay? Now, we know if you have some quantity of thermal energy being exchanged with the surroundings, the magnitude of delta S of the surroundings is inversely proportional to the temperature of the surroundings. Okay? Meaning, higher the temperature of the surroundings, the thermal energy that is emitted by some kind of process or reaction is going to have less of an effect. So it's informally, not inversely proportional, okay, to the temperature. So delta S is inversely proportional to the temperature and directly proportional to the heat. So combining those proportionalities, we can get this particular expression. Delta S of the surroundings is inversely proportional to temperature, directly proportional to the heat released by the system. Okay, we know that heat under constant pressure is enthalpy, so we can replace Q with H. So read it carefully. For any physical or chemical process occurring at constant temperature and pressure, the entropy change of the surroundings, delta S of the surroundings, is equal to the energy dispersed into the surroundings divided by the temperature of the surroundings in Kelvin. Okay? Because the temperature of the surroundings is what matters. When I say temperature is constant here, that is the temperature of the system. Okay? So, the thermal energy released by the system, or the delta H of the system, divided by the temperature of the surroundings, is going to give you a value for the delta S of the surroundings. Okay? That is a little expression that we can come up with based on the variables that we know so far. This expression explains why exothermic processes have a tendency to be thermodynamically favorable. They do tend to be thermodynamically favorable. However, as the temperature of the surroundings increase, a given release of thermal energy produces a smaller delta S of surroundings. So exothermicity, mouthful, becomes less of a determining factor for thermodynamic favorability. Okay, the hotter the surroundings, the less effect that the thermal energy released has in changing the entropy of the surroundings. So exothermic reactions, it's hard to determine why some of them are thermodynamically favorable based on this particular expression alone. Okay, so enthalpy is not a good determining factor, entropy alone is not a good determining factor, or entropy of the surroundings is not a good determining factor. So we're trying to work our way towards what really tells you that something is thermodynamically favorable. Okay, now let me do a time check because I'm actually in class right now. We are at 2:38. So, you guys good so far? Right? Okay. So, here's an equation. I'm not going to do the math for it. I'll just tell you the signs for it. You can do the math because you really don't need to do the math here. Okay. You have a way of calculating entropy changes in the surroundings. So, you can calculate the delta S of the surroundings based on the expression that we saw earlier, delta S of the surroundings is equal to negative delta H of the system, as long as the system is at constant temperature and pressure, divided by the temperature of the surroundings. Okay, so I have, usually the system and the surroundings are at the same temperature. Okay, so I have this reaction happening at 25 degrees Celsius or 298.15 Kelvin. Remember, Kelvin is used because the units for entropy is joules per Kelvin. Okay, so if you calculate this, this is going to be negative, the delta H is negative 2044 kilojoules over 298.15 Kelvin. That's probably going to be like six or seven, close to 7. Okay, so that's still going to be a positive value. So we can say that the delta S of the surroundings is a positive value. Okay, it's a small positive value, but it's still a positive value. Then you can determine the sign for the delta S in terms of kilojoules. It's small, but in terms of joules, it'll be like what, 6,000-ish. Okay, so you are able to determine the sign for the delta S of the system. Now you might be like, wait, how do you calculate that? You don't have to. You just look at the reaction and you can tell if the delta S of the system is positive or negative. You have 1 plus 5, 6 moles of gas on the reactant side. You have 3 plus 4, 7 moles of gas on the product side. Increase in moles of gas or increasing number of particles means you have a plus delta S here for the system. Okay? We know that the delta S of the universe is the sum of the delta S of the surroundings and delta S of the system. If both are positive, delta S of the universe is going to be positive. And is the reaction thermodynamically favorable? Yes, it is. Okay, so that's how you would figure out what what the delta S of the universe is in this kind of scenario. All right. So that's short video on just entropy. The next one is going to be about free energy. That is really important. So pay a lot of attention. Okay.